Okay, so now we're back and we're going to talk about the perpendicular transversal theorem. If a transversal is perpendicular to one of two parallel lines, then it's perpendicular to the other line as well. So, might seem common sense. If basically it's saying if M is perpendicular to N and these lines are parallel, well, it's going to be perpendicular to P as well. You might say duh, but remember we're practicing our two-column proof skills, right? That's a big punchline, all right? And then looking at some more notation before we start this proof. Remember the upside down T means perpendicular, so this reads line M is perpendicular to line N. All right, so let's fill in or draw on our picture to see the exact information. Kind of already did, but let's redo it. Lines are parallel, and that's perpendicular to that. Actually, let's do it like this. That's perpendicular to that. All right, so reason one given. Angle 1 is a right angle. Again, sometimes we encounter new stuff, but we'll see it a lot. But this would be definition of perpendicular lines. All right. The definition of perpendicular lines are two lines that intersect to form a right angle. So angle 1 is a right angle by definition of perpendicular lines. So basically, emphasizing some stuff, we have buzzwords, we have perpendicular lines, so we're going to talk about it. Similarly, in this next one, we have right angle, so we're going to talk about it. What do I mean by that? How do we know the measure of angle 1 is 90 degrees? Well, it's just definition of right angle. If it's a right angle, its measure is going to be 90 degrees by definition. All right, now, how are angle 1 and angle 5 congruent? Well, again, it's just corresponding angles. Postulate. Okay, so what we're going to do from here, again, being tedious, being precise, being exact, being thorough. Let's say the measure, if they are the same angle, their measures must be the same as well, by definition of congruence. Cool. All right, so what can I figure out from here? I know angle 1's 90 degrees. I know angle 1's congruent to angle 5. I know measure of angle 1 equals measure of angle 5. Well, based off all this stuff, if 90 degrees equals angle 1, angle 5 equals angle 1, measure of angle 5 must also be 90 degrees by transitive. Okay, so again, the definition of right angle is a very strong definition. That means I can go either way, so I know angle 5 is a right angle by definition of right angle. And again, that just comes from biconditional statements. Since it's right, I know it's 90. Since it's 90, I know it's right. Because right angles, an angle is a right angle if and only if it's 90 degrees. All right? And then again, we should never miss the last statement. These lines are perpendicular. Why? This might blow your mind, but it's just by definition of perpendicular lines. Okay. If two lines are intersecting to form a right angle, in this case right here, M is intersecting P, 5 is a right angle, so they must be perpendicular by the definition of perpendicular lines. That's it. Wow, cool, neat. All right, so why did we learn this? Why is this so powerful? Well, this is all the buildup to the mighty triangle. All right, we talk about triangles a lot in this class. The second half of Unit 4 is all about triangle congruence. Unit 5 is called triangles and their properties. In Unit 6, we talk about similarity, but we focus on triangles a lot. Unit 7 is called right triangle trigonometry. And when we talk about polygons in the future, a lot of it just comes down to triangles, all right? So if you love triangles, you're gonna love this class, all right? We talk about them all the time. And if you can really just understand, master the triangle, a lot of things come with that, all right? So we're still kind of building up to the triangle, all right? So I copied and pasted this from the internet, but I thought this was good stuff. So triangles are particularly important because arbitrary polygons with 4, 5, 6, or n sides can be decomposed into triangles. So like watch this. Here's a square. I can make it into 2 triangles. Here's a pentagon. That's not a pentagon. Anyways, pretend that's a pentagon. I'm struggling with technology. I can make it into just 4 triangles, all right? I can take any shape and just make it a bunch of triangles. That's for polygons. Thus, understanding the basic properties of triangles allow for a deeper study of these larger polygons as well. But triangles aren't just mathematically significant, they are also fundamental to the way we build our environments, both physical and virtual. Triangles are special because they are exceptionally strong. All right, triangles are strong. Out of all the 2-dimensional shapes we can make out of straight struts of metal, only triangles are rigid. Now, I'm sure you've had a teacher tell you this at one point in time where, like, you can't push over a triangle like you can a square or some other shapes. All other shapes can be deformed with a simple push if a shape is hinged at the corners. For example, a rectangle can be pushed over into a parallelogram. So that's basically saying if you have this rectangle and you're strong enough, you can push the sides over. And, like, that side would still be X, that side would still be Y. They would still have the same lengths. All right, but not the trusty triangle. You can't push over the trusty triangle, which explains why it's I struggle to pronounce goofy words. Ubiquitous use in constructions from pylons to bracing, like the word calligraphy. I can never say that word as well. Calligraphy, that fancy pen. I get tongue-tied easy. But anyways, that's why power lines look this way. A lot of buildings, like look at next time you're at a Derby football game under the bleachers, there's a lot of just triangles there for supports. All right, so watch this. I'm just going to start rambling, but this is a powerful picture. This might be one of the most important pictures in geometry itself. All right, let's do statements, let's do reasons. All right, we're going to prove that, let me say this. We're going to prove that measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180 degrees. All right, and we're given, what do we need to be given? Let's just say given AD is parallel to CB. All right, so this isn't this isn't formatted officially, but let's just format it like this. So we're given these lines are parallel. Let's prove that the interior angles of any triangle add up to 180 degrees. All right, we'll do this again later, but it just directly relates to what we're talking about now. So that's why I wanted to take time. All right, so what's so powerful about what we did today, and again, we'll go back and forth, but once we prove a theorem, we're able to state and cite that theorem throughout other proofs, all right? Rather than having to prove the vertical angle congruence theorem or the other theorems we prove, such as the AIA. We're able just now to cite them. What do I mean by that? Since AD is parallel to CB, I can say, well, angle 1 and angle 4 are congruent. Why? Because they're alternate interior angles congruence theorem. I'm just going to write therm. And similarly, I can say the same thing for angle 2 and angle 5. Because if I extend this other side AB, as a transversal, we can say that 2 and 5 are also alternate interior angles, just a different transversal. Now, how do I want to state this? Without being too lengthy, let's say the measure of angle 4 plus the measure of angle 5 plus the measure of angle 3 equals 180 degrees. And again, this isn't official, this is just kind of a rough draft. We're officially going to do it later. But we're just going to say they're a linear triple. Linear triples aren't real, but do you see how we have 3 angles? It's like a linear pair. They're forming a straight line, like we could say 3 and 5 forming a linear pair with 4. Let's just make up a linear triple. And actually, I can bring up this last statement now because, again, this is more of a chicken scratch proof, not official, but I can substitute 4 in for 1. I can substitute, 5 in for 2. Again, that should say congruent up there. And now I've proved that the interior angles of any triangle add up to 180 degrees. All right, this was a rough draft. That's just a little foreshadowing to what we're going to do in Unit 5, but that's why we're learning this right now. We'll be a little bit more official in the future, but isn't that powerful? That's how we know triangles add up to 180 degrees. If you ever wondered, how do we know this? How does this work? Well, we can prove it, and that's why. All right, and that's really important because, again, this is how we build buildings. This is how we build structures. All right, we know this works. We've proved it to be true. So we're confident that the parking garage made out of tons and tons of cement isn't going to fall on our head, or the houses we live in, or the schools we go to. All right, we're going to do some algebra in the next video, so stay tuned for more.